Hello. As mentioned before, I'm Matthew Waters. I am here to talk to you about GStreamer WebRTC and why it is the most flexible solution to a lot of web-based media. So, to start with an introduction, I am from Newcastle in Australia. I've been there all my life. Born in Canada though, which is an interesting tidbit. I work for Centricular, which is a consultancy mostly around GStreamer. Done a lot of things in that area. Previously, before this WebRTC adventure, was in graphics, so OpenGL and Vulkan. I am the current maintainer of those plugins in GStreamer, or their integration both with applications and in elements and plugins, etc. These days, I'm working on WebRTC, which is the whole why I'm here to talk to you about it. So, how many people do know about GStreamer? That's about half the room. How many people of those have used it to build something or tinkered around with it? About a quarter of the room. Okay, so for the other people in the room, GStreamer is an open source, cross-platform, extensible pipeline-based media framework. That is a lot of words that mean a whole bunch of different things. So that jargon essentially means that open source, it's all open. Most of it is LGPL, BSD, MIT, all those kind of things. The development's out in the open. There's a community around all of it. There's also commercial support if you so desire. Cross-platform is supports all the major platforms, Linux, Android, Windows, macOS, iOS. We ship binaries for everything except for Linux. We rely on basically distribution packages for all of that. So you can use it to build applications on mobile and embedded devices all the way up to large data center server applications. It's extensible by virtue of its design. It is based on a plugin architecture where there are specific blocks or elements that you can plug together to produce and process data. Mostly media data, but not restricted to media data. One example of using non-media data is the LIGO gravitational wave analysis project that used GStreamer to detect gravitational waves. And the other bits I have looked in. So we integrate with a number of different frameworks and toolkits for decoders, demuxers, streaming, covered by a whole bunch of different API. GStreamer is a large framework and it can do a lot of things. And sometimes you may actually need some guidance in navigating that framework. If so, please feel free to chat to me afterwards about that. We provide a somewhat consistent interface for integrating with or accessing different classes of elements. So decoders or encoders have generally a specific interface that you can generally rely on. There is also a high-level API for accessing specific tasks that you want to do. For example, a media player versus a nonlinear video editor have different use cases and scenarios they need to do. For media playback, there is a GST player API. For the nonlinear video editing, there is GST editing services. Yeah. This is a caveat on what GStreamer is not. It basically means that it is not the actual application itself. It's a framework for building all of these applications. Yeah. There are debug tools and helpers that implement most of these things, but our focus is not on building those applications itself, where our focus is on enabling other people to build these applications. So I started my WebRTC work about 3 years ago with the OpenWeb WebRTC implementation. OpenWeb WebRTC is a GStreamer based, but it was mobile focused and client focused. My experience with that was with developing hardware acceleration for video encoding and decoding. It wasn't precisely on the WebRTC protocol itself, but that was my first introduction to it. The next adventures were a little more interesting and involved actually dealing with WebRTC in and of itself. So the first one was on an embedded Linux device, trying to use their hardware decoders, using that efficiently. The specific device was an IMX6. The WebRTC.org codebase was an interesting beast in that such things are difficult to implement in a performant way. The next one was actually on a server-side application, specifically trying to design basically a forwarding gateway server for a WebRTC with multiple clients. Then the next one, which I'm talking to you about today, is the GStreamer-based implementation that is upstream now. So the web, history of the web is a long topic. The idea with a lot of the newer standards in HTML5 are to allow use cases that were only really viable with a native application. So the addition of video and audio playback in HTML5 is a direct response to such things. And the idea is to provide tools that web developers can use to build things that may only have been provided by a native application. Whether that's rendering APIs with WebGL or 2D Canvas API, those such things came about due to the need for allowing JavaScript and web developers to do native applications in the web. One of these things that native applications do is video conferencing. And WebRTC was the WebRTC group inside various standard bodies was created in order to combat and enable this use case inside of a web browser. So the idea is real-time communications. It's a tool for enabling the building of pretty much any video conferencing solution inside a web browser. It doesn't provide the full experience. The provider or whoever is developing the solution needs to implement some part of the information and processing that is needed. That part is a rather small part and actually rather depends on what experience you're trying to expose to the end user. The one limitation of the WebRTC spec is that it is a peer-to-peer connection. So multiparty is not specifically supported, but as we'll see later, it is possible to do in a reasonably efficient way. Currently, it's still in draft, although I think 6 months ago, they announced they were proposing it for a candidate recommendation, so it is stabilizing. I believe the last thing on the roadmap before stabilization is simulcast. Everything else is pretty much set in stone and won't change, and any new features or additions to WebRTC will be in further versions, such as WebRTC 2.0. Used for video conferencing, can also be used for arbitrary data transfer. There is primitives for enabling that. That is called data channel. The other side use case is real-time playback in a browser or preview without requiring JPEG. If you've been to the Open Hardware Mini Conference, these donkey cars that are around, their control interface on the web in the website is based on Motion JPEG. This WebRTC could be used instead. This is a diagram of the layers involved. So you have two peers trying to connect to each other, trying to stream media between each other. The WebRTC part is in the browser, and they expose different session descriptions, which is basically a list of attribute pairs that have a special format to the app that needs to be transferred to the peer. That signaling protocol is the little bit that needs to be implemented by the application based on what user experience you're trying to expose. Everything else, transferring media, transferring data, the connection setup is all handled by the WebRTC implementation itself outside of the application. So, multi-party. As mentioned before, WebRTC is strictly a peer-to-peer thing. So, in order to support multi-party in like conferencing networks, there are three main models. There's the mesh model, there's the SFU, and the MCU model. These are some providers that provide different implementations and use different multi-party solutions. Some of these can be a little blurry. For example, PEXIP actually does both SFU and MCU. So, to go into detail with these three models, the mesh model is where each client has to send their stream to each peer, and each peer receives a stream from each client. As you can imagine, this is not very scalable in terms of both bandwidth and processing. You need to send a lot of data to each peer for large number of users. For 10 users, you need to send 10 streams and receive 10 streams. Then you need to mix those 10 streams together or discard them, however your experience is. The cost for the provider is relatively cheap. They have pretty much a constant cost of basically setting up the call. The other extreme is where there's a server in the middle. That is essentially every peer sends and receives one stream from. And that server would mix either one stream for every peer or can mix different views for each peer. This is, of course, higher complexity for the provider. It needs to deal with connecting to every single stream, but it is rather cheap for the user and end device with only one stream in and out. There is a sort of middle ground. The idea with this one overall is that the bandwidth cost is higher than the processing cost, especially on edge devices that may be on a 3G network or possibly even 2G in some cases, out in rural, for example, Australia, where the NBN is an interesting development. The idea with this is that you send your stream to a central server and then it forwards that to every other peer. So for the provider, for the client, the cost is relatively contained, and for the provider, the cost is also relatively contained. This approach means that the provider is not mixing per se, it's just forwarding packets from one client to another client. This is a complexity table of all the different approaches. As mentioned before, for mesh, the provider bandwidth is relatively constant. We're just setting up the signaling. The all user bandwidth n factorial is a large number for a large number of users, so that is generally a bad idea, especially with bandwidth constrained edge devices. And depending on how the provider is exposing their end experience, the MCU can be expensive in terms of video mixing all these streams together. So with any, well, the ideal goals and motivation of any solution involving WebRTC would be to support all these use cases, both the client side with an edge, like small Raspberry Pi exists, for example, and allowing implementing server-side applications that can forward or mix these streams together. For that, you probably want to make use of hardware-accelerated encoding or decoding, and you want a sane API for implementing such applications. Previously, there were existing WebRTC solutions based on GStreamer, OpenWeb WebRTC, which I've mentioned before, mobile first application framework. The server side, let's go with OpenWeb WebRTC first. So it started out as an Ericsson research project, proof of concept. It's client-side based, so it does not support the necessary things for implementing forwarding things for a SFU, selective forwarding unit. It does support hardware-accelerated encoding and decoding on Android and iOS. The iOS part is and was more featureful and tested than the Android side. It has a custom signaling wire format, so it basically splits up what a browser SDP into its own format. At this point is effectively unmaintained, so for new applications it's probably not a great idea to use it. Curento is the server side of this. So it is designed as a server application, basically for mixing or forwarding, WebRTC streams. It is based on a rather ancient version of GStreamer, however. They have custom patches and things, and they have their own bin elements, and it uses its own signaling API, so you're locked into that as well. There are, looking at other WebRTC implementations, the other main one is WebRTC.org, which is used by all the browsers. Janus is a WebRTC gateway. It deals with signaling. That's pretty much it. All the media is produced through plugins, and then there are a whole bunch of SIP gateways that integrate with, for example, audio conferencing to a web browser. So WebRTC.org is the most featureful. It's used by all the major web browsers at this point. Chrome, Firefox, Opera, which is a Chrome UI at this point. With the announcement that Microsoft is basing their web browser on Google Chrome these days, that means they are also using will be using WebRTC.org. Previously, they had their own implementation. This means that pretty much all the web browsers are using this implementation for implementing their WebRTC needs. As a result, it's designed for web browsers, which means that using it on a server-side application is hard, and it's not designed for that. So things like forwarding WebRTC streams without decoding or encoding them is, last I looked, impossible. The other thing is that the API is constantly changing. With one of the projects I was working on, over the course of around 6 months, the API changed in integrating encoders and decoders a couple of times. They only define zero copy path is with as defined on Android with OpenGL textures. Anything else is basically you have to write your own patches to implement that. Apart from that, everything else is raw media. So you cannot forward RTP streams you cannot forward a already encoded stream to another stream as you would need in a SFU. Janus is a generic WebRTC gateway server where the core deals with signaling and all the media is implemented through plugins. So, and the other thing is that it also requires its own signaling API, which seems to be a common trend in all these solutions that are involved. There is a streaming plugin, so you can send GStreamer encoded video to Janus and have it be picked up by a normal WebRTC client. However, that is exposed through a known UDP port that you have to configure, which means that you are traipsing through the kernel a couple of times, and the feedback on do I need to send less data, more data, can I send more data, it does not exist. And dynamic, like adding or removing streams, is not currently supported by such a plugin. So, for example, you have a video conference and you want to also share your screen. That is a dynamic reconfiguration change that would need to be done. Such thing is not easy to do with Janus. It's generally for fixed scenarios, essentially. If you want to look at that, there is a blog post there that outlines how to set such thing up. So, we're looking for a solution that covers both the server side forwarding use cases as well as looking at embedded devices and doing things performantly. From all of those solutions I've outlined before, none of them actually fit that. So, what do we need to do that? First thing we need is RTP. All media in WebRTC is transmitted using RTP, which is real-time transport protocol, of which there is an already existing element called RTB bin in GStreamer, which is already used for other things like RTSP and even just raw RTP over UDP streaming. The connection setup is organized through ICE, which is Interactivity Connection Establishment. It deals with opening up ports on a UNP-MP compatible router, punching holes through NATs. If all that fails, then you can also use a relay server, which is called Turn. The other thing is that you want your media and information to be encrypted while it's being transported over the internet. That is through DTLS and SRTP. DTLS is a datagram TLS, transport level security. It encrypts. It's very similar to normal TLS as used by HTTPS. SRTP is used to negotiate the keys. It's actually the other way around. DTLS is used to negotiate the keys, and the SRTP is used to encrypt your data in the RTP transport. The That's for audio and video. For arbitrary data, there is a separate transport, which is SCTP, which also runs over the same connection establishment called ICE. SCTP is Stream Control Transport Protocol, which allows you to choose how you would like your information to be sent. In terms of reliability, whether it will be ordered or unordered, basically having the option of choosing between UDP or TCP or some combination thereof in between. We also need some kind of API to use. This is conveniently provided by the W3C consortium via the peer connection API, which is standardized through various standards groups. The browser side of that is outlined in something called JSEP, JavaScript Session Establishment Protocol, and outlines how a browser, WebRTC compliant browser will behave when setting up a stream, adding streams in a WebRTC context. The exchange of connection information is done through SDP, Session Description Protocol, and we also need a way to basically pass and generate compliant SDP for the web browser to use. So we built this. The element is called WebRTC bin. It does a lot of these things. I don't know how many of you are familiar with GObject, but there are properties and signals that are on WebRTC bin that allow the WebRTC setup call flow to occur. That's a helpful blog post that was written in order to explain the scenarios and how basically how the thing works in an overview sense. So the goals of WebRTC bin would stick to an API that's close to the peer connection API as standardized by the standards groups in order to avoid learning two separate APIs that you need to match together. We've stuck pretty close. I mean, there are some naming differences. For example, GStreamer uses underscore case, whereas the spec uses camel case. We stick to our own GStreamer case. Apart from naming things, the API is reasonably similar, that you can compare them very, very easily. As mentioned before, the gateway and full stack use cases are supported. So for server side, you have one WebRTC bin per client you want to connect to, and then you connect those all together in however way you would like to mix or forward the streams to other peers. Another goal that is currently not implemented at the moment is dynamic number of streams, so adding and removing streams while the connection is ongoing. That is still a work in progress. Currently it's mostly static. I do have work in progress to add something in the way of dynamic number of streams. The other reconfiguration of a call is changing media codecs, which is also another thing that would need to be done. Needs to be looked at. The other thing is connection statistics, in that an edge device may fall off the network. And you need to be able to detect that, take preventative measures, or expose saying it fell off the network to maybe the peer or to a central server if you have access to it at that point. So providing connection statistics on whether it's there, how much is it there, how fast is data being transported between the two peers. Those kind of things are useful metrics in order to dynamically reconfigure how you're going to be doing things. So what can it do at this point? It can do all of them. Only the first one is in a stable release. All of the others are currently in master. So in order to use anything other than just plain audio and video streaming, you would need to build a local checkout of GStreamer in order to have RTP bundling, data channels for sending arbitrary data. RTP bundling is interesting in that the idea is for sending n number of streams over a single connection. So all your media and data is transported over a single connection. Ideally, that reduces the setup time because you don't need to set up n connections via ICE, which may all go through the same relay or need to open n ports on your NAT or through your firewall, etc., etc. Forward error correction is useful with lossy networks, as is very prevalent over the internet. The idea is to send extra data to the peer, so if packets are lost, then the extra data can be used to reconstruct the original data. That, of course, imposes an overhead in what you're going to be sending. And depending on the network, either results in better or worse performance, pretty much. And is a rather open research question as to what you should be doing in terms of forward error correction. The other loss mitigation technique is retransmission. So retransmitting a lost packet if available. For example, that. Unified Plan SDP, the other SDP format is called Plan B, which is currently used by Google Chrome. Firefox uses Unified Plan SDP. The difference between these two SDP formats really only comes about when you're dealing with multiple streams of the same type. So if you have multiple video streams that you're trying to send, that would result in different SDPs that may or may not be passed and implemented correctly, depending on what you're using. If you're only sending one audio and one video stream, then that doesn't matter. So as in the specification of WebRTC, the SDP is the signaling exchange format. WebRTC being exposes SDPs as connection information that you need to send to the peer. And the peer would take that and produce an answer SDP that you would set on yourself. Currently, that's constructed from sync pads and caps. So each element in a GStreamer pipeline has pads that connect to other elements. The capabilities on each sync pad is used to produce the SDP that you send to the peer. ICE candidates are sent to the peer. Basically, what can I use to connect to? What can the peer use to connect to myself? Those kind of things. Pads are exposed depending on what is happening. Data channels are exposed as an object, which is also the same as the specification that you can call send a message and receive messages, as well as get notifications about errors, whether the data channel is open or not. That's, if you know WebRTC itself, then those kind of things map relatively well to the GStreamer side as well. So hopefully we have a demo. Let me just get step 1. So this is a demo, as obvious. The idea is that this GStreamer implementation is attempting to talk to a web browser in the other side. So hopefully if the internet works well enough, and of course it doesn't. Power button. And you can see GStreamer is producing a stream that the web browser can read. Due to some interesting issues with duplicating things, let's try this again. And in theory, you need to click the allow. We also have the browser sending stream back to us from the video. It's cool. That example is here, so you can run that yourself if you would like to. There are also some tests. The examples are written in a number of languages. There are Python, Rust, C, and C# versions. There are also test applications in GStreamer itself that outline different approaches to how you might want to do things. So testing, there are some unit tests for various SDP formats, etc., etc. And looking into integration testing, I have some examples of that. If you would like to see them, catch me afterwards. These kind of things, yeah, at the moment we don't have time for that. So this is what would be next. The big one is reconfiguration, so enabling, for example, video codec changes at runtime, as well as adding and removing streams from a session, as well as congestion control. That's currently not a supported feature of WebRTC bin, as in reducing the amount of bandwidth that is produced or bit rate of the encoder, etc., etc. Yeah, thank you.
Hey, how much of WebRTC bin can we use without the SDP signaling? Like, can we use our own external signaling and just hook into it to get info about codecs and pass them around outside? So there's a couple of protocols that will use their own signaling outside of SDP. So some protobufs, for example, for Hangouts to be able to pass around codec information and ports and things. Is it possible to get access to that info through WebRTC bin, or is it kind of a black box in that regard?
Is your question is whether you can get access to what, encoders or decoders? Is that your question?
Yeah, so information that would normally be part of the SDP packet, can that be pulled out through the WebRTC bin?
That's not exposed through WebRTC bin. That is exposed through GStreamer itself. So elements like a video decoder expose that they are a video decoder, for example. So you can iterate over all the elements and just check all your video decoders or encoders, etc., those kind of things. Does that answer your question? Okay.
Thanks very much for clarifying a whole bunch of different sort of schema things in my own mind that I didn't really understand before. I have been desperately looking for a WebRTC-based replacement for something like Zoom, which I think I want to use an entirely open source communication stack. And I'm wondering, by giving the names like the mesh and the SFU and the other one, I forget what it is off the top of my head, but I'm wondering, I noticed that you didn't include Jitsi in any of your examples of existing implementations. I don't actually know where it sits amongst these, and I'm also wondering if GStreamer and the WebRTC bin offer any hope to achieving the kind of star model of communications as opposed to the mesh in a performant way.
Okay. I'm not sure where Jitsi stands. You might be able to look it up, but I don't know personally. As for a star configuration, where you have basically multiple servers that you would be routing data through, GStreamer WebRTC bin can do that. You would need to basically code that up yourself, but it can be done.
Thanks, Matthew. I'm working on some IoT problems that involve remote monitoring. Am I going to cry tears of blood if I try and run this kind of stuff on things like Raspberry Pi class systems? How much, I guess, compute power do you need to get a decent video feed?
The compute power required is mostly dependent on the encoders and decoders that are in use. So for the Raspberry Pi, for example, Yarn has an example that can read from the camera, the Raspberry Pi camera, use the hardware encoder, and then send that to a WebRTC stream. I think he has it up here with him. It's up there. You can go, he's up there. He has that.
Excellent. Cool. Thank you very much.
Hi. I was wondering if there is an element in GStreamer which, like this, would talk just SIP.
There is a SIP, SDP demux element, but I don't believe there is a ready-made, Yarn has an answer to that.
SIP is bigger than the codecs that sit underneath. There's a lot in common between WebRTC and SIP once the streaming is set up.
Could you repeat that name again? Fast. F-A-R. Okay. Thank you.
Any other questions?
Hey, I'm just wondering, I know WebRTC's got lots of stuff in it for getting around NAT and things like that. Do you know if this stuff would work all right on a private Wi-Fi network that doesn't have internet access? Or do the browsers depend on having internet access to get to this stuff?
I don't believe they require a outside access to the internet. I think one of the first ICE candidates they produce is the local network address. So if you can talk over the local network, it should work.
Any more questions? If not, in that case, I'd ask you to show your appreciation again to Matthew.
Thank you.